Chapter 18: Kinetic Theory of Gases. These topics will be followed in this chapter: the ideal gas law and the molecular interpretation of temperature, distribution of molecular speeds, real gases and changes of phase, vapor pressure and humidity, van der Waals equation of state, mean free path, diffusion. Let's start with section 1, the ideal gas law and the molecular interpretation of temperature. Assumptions of kinetic theory include large number of molecules moving in random directions with a variety of speeds. Molecules are far apart on average. Molecules obey laws of classical mechanics and interact only when colliding. And finally, collisions are perfectly elastic. It means that they are not losing energy and they are bouncing back with the reverse momentum. All right, here we have a cubical box containing the molecules or atoms shown with the sphere and the green arrow representing their direction of velocity and motion. The size of the cube, one side is L, and the area of one of the sides is capital A. And if you want to calculate the force exerted on the wall by the collision of one molecule, we can say, as you remember, the definition of the force is the change in momentum, delta P, or P momentum is mass times velocity, mv, divided by delta T. So force is written as the changes in delta of mv divided by delta T. And if you remember, delta P was mv, mass times velocity, and we said for the elastic collision that we're assuming here, the masses and the velocity do not change, only they change the momentum direction. So we will have mass is fixed, velocity final in x direction, minus velocity initial, which is the opposite direction, still in x direction, and we assume, let's write it down here, velocity final is equal to minus velocity initial, and the absolute value is the same, let's call it v, and it's equal to 2v. So we have 2 mv, x is the velocity along x direction, and we can write down this equation for changes in momentum along y and z direction if you want to say forces applied on each of the plane. But for the plane of A, which is normal to x-axis, we're only talking about changes momentum along x direction. Okay, so the force due to collision of the atoms applied on wall that I just showed it here with the dashed lines is equal to 2m v sub x divided by delta t, and delta t, let's erase this stuff here, delta t from the equation of motion is equal to L divided by v sub x divided by 2. Okay, or we can say this is equal to 2L divided by Vx. And we call it 2L because the path is moving 1L in this direction and 1L the other direction, so we'll have 2L. Putting all together, F will be equal to mv sub x squared divided by L, and that is the force applied on wall with the surface of capital A, and we can sum over all the forces on all molecules colliding with that wall. We should sum it over the velocities, and we can average over all of them, and we can write it down as m divided by L multiplied by capital N, which is the number of molecules inside this box which are colliding with the wall, and they have all average velocity of v sub x, and the bar on top of it shows the average velocity. To consider the averages of the forces applied on all the walls of the cubical box that we mentioned in the previous slide, we can sum over squares of the components of the velocity. So we say, let's write it down here. So we say v squared total is equal to average is equal to the average of the velocity along x direction plus average of the velocities along y direction plus average of the velocities squared along z direction. And the velocities are assumed to be random, so there is no direction of preference, and we can say v sub x squared mean is equal to v sub y squared mean, and is equal to v sub z squared mean, and we can call it the mean of v squared is equal to, and if all these three are equal, so we can call it 3 v sub x squared average. And if we plug these into previous equation of the previous slide, F is equal to m divided by L multiplied by n, the number of atoms or molecules inside the box. And instead of v sub x squared mean, we will have the v, the average mean squared of the velocities divided by 3. Okay, let's erase this stuff here very quick. Okay, so pressure is defined as force applied on surface, right? The force is given here. The surface is, for a cube of size L, is L squared. And if we divide F by L squared, we will have L cubed in the denominator, which is equal to L cubed, which is volume. Pressure is 1/3 times N times mv squared average divided by volume. To gain more insight, we can rewrite the previous equation in terms of the ideal gas law. If you remember from the ideal gas law, we had PV is equal to N, capital N, times K, Boltzmann constant, times T. And on the other hand, we have from the previous slides, we had P is equal to 1/3 N m v squared mean divided by volume. So if we write down this equation, multiply both sides by volume, we will have PV is equal to 1/3 N m v squared mean. Also, if we pay attention that we have mv squared, and if you remember from kinetic energy, this is the mean of the kinetic energy, and we can write it down as 1/2 mv squared average. Okay, so if you plug in this value into the equation for PV, we will have PV is equal to 2/3 N potential energy mean. Okay, that's what we have here. This is the mean of the kinetic energy. Compare it with the ideal gas law. We can find the mean of kinetic energy is 1/2 mv squared mean, or is equal to 3/2 times Boltzmann constant K times temperature T. The average translational kinetic energy of the molecules in an ideal gas is directly proportional to the temperature of the gas. So that's what we gain from this equation. Mean of K, or kinetic energy, is directly proportional to temperature, T. This is important. Now, using these definitions and calculation, we can now calculate the average speed of molecules in a gas as a function of temperature. V sub RMS, root mean square, is the square root of V squared mean, and it's equal to the square root of 3kT divided by m. As an example, let's look at problem number 8 from the book. At what temperature do the atoms of helium gas have the same RMS speed as molecules of water vapor at 20.0 degrees Celsius? To solve this problem, we have to look at the equation for the RMS speed. And we notice that in this equation, the speed is related to the Kelvin temperature. So we can say V RMS of helium is equal to, that's what we want. We want to have the VRMS of helium to be equal to VRMS of H2O, water, the vapor form. If you write down the equation on the left hand side, we have the square root of 3k T of helium divided by mass of helium is equal to the square root of 3k temperature of water, or H2O, divided by mass of water, or H2O. Let's be consistent. It's the water, let's write H2O. Okay, if we raise the power of 2 for both sides and make it squared on both sides, we can have 3k T of helium divided by mass of helium is equal to 3k T of H2O divided by mass of H2O. And you will see 3k can cancel out. You can write it down as temperature of helium is equal to mass of helium divided by mass of water multiplied by temperature of water. And if you plug in the numbers, temperature of helium is 4.003 atomic number divided by 18.01 atomic number multiplied by T of water in Kelvin. So we have 273.15 plus 20.0 degrees Celsius, and this can be converted into 65.15 Kelvin, or we can write it in degrees Celsius as minus 207.99 degrees Celsius. It's roughly equal to minus 208 degrees Celsius. Okay? Alright, section 2. Distribution of molecular speeds. The molecules in a gas will not all have the same speed. Their distribution of speeds is called the Maxwell distribution. And it's written as F of V, or velocity distribution, or function of V's, is equal to 4 times pi times n times m divided by 2 pi kt all to the power of 3/2 multiplied by v squared times exponential of 1 minus 1/2 mv squared divided by kt. Here k is the Boltzmann constant, and here is the same. T is the temperature, m is the mass of atoms or molecules, n is the number of atoms or molecules, v is the velocity, and the same as m is here, and v is the velocity, and t is the temperature. Now down below, if we look at the distribution or the probability of the velocity distribution, so on this axis we will have the relative number of molecules of Fv, or the probability of the atoms that had different velocities. On the horizontal axis we have velocity or speed, We have V sub p, which is the most probable, or the peak of this distribution here, the most probable speed. It shows us how many of these atoms have that speed. And then we have V mean, or V bar, and then we have V RMS, or the root mean square of the velocity. So the Maxwell distribution depends only on the absolute temperature. The figure below, which is here, shows the distributions for two different temperatures. At the higher temperature, the whole curve is shifted to the right. Okay, so this is the first curve at 0 degrees Celsius, or 273 degrees Kelvin. And the second curve is at 310 Kelvin, or 337 degrees Celsius, which you can see this is shifted to the right, to the higher speeds. So that makes sense. If you have more higher speeds, or if you have higher temperature, we have more activities of molecules or atoms, and they have more distribution of higher speeds. So the whole curve will be shifted to the higher speed to the right. Now we're going to look at problem number 20 from this chapter, from the book, as an example. A group of 25 particles have the following speeds. 2 have a speed of 10 meter per second, 7 have 15 meter per second, 4 have 20 meter per second, 3 have 25 meter per second, 6 have 30 meter per second, 1 has 35 meter per second, and 2 have 40 meter per second. And these are the speeds of these 25 particles. Determine A, the average speed, B, the RMS speed, and C, the most probable speed. So to take the average speed, we have to write down average velocity, or speed, as 1 over n, the sum of VI. And Ni means the number of atoms or particles with velocity VI. Okay? And the sum of I is from particle number 1 to particle number 25. Okay? So we will say we have 25 particles. We have 2 particle speed of 10 meter per second plus 7 particles of 15 meter per second. We have 4 particles at the speed of 20 meter per second plus 3 at the speed of 25 meter per second plus 6 particles at the speed of 30 meter per second and 1 particle at the speed of 35 meter per second. And last, we have 2 particles at the speed of 40 meter per second. And if we sum them up, divide them by 25, let's check if I'm not making any mistakes. So we have 2 at 10, 7 at 15, 4 at 20, 3 times 25, 6 times 30, and 1 has 35, okay, and we have 2 at 40. Okay, so if we do the math, we will have 23 meter per second. So this is the part A, the average speed. Now for part B, it talks about the RMS, or the root mean square. We call it VRMS, and this is equal to the square root of 1 over n, sum of I from 1 to 25, Ni, but this time we have Vi squared, because this is called root mean squared, so we need the velocities squared. And if we write down the same story, the square root of 1 over 25 times 2 times 10 to the power 10 squared meter per second squared plus 7 times 15 meter per second squared, 4 times 20 meter per second squared, 3 times 25 meter per second squared, 6 times 30 meter per second squared plus 135 meter per second squared plus 2 times 40 meter per second squared. Close the square bracket, and everything is under the square root. And if we do the math, what we will have is 24.56 meters squared, or roughly 25 meter per second. Okay, so this is the RMS speed. For part C, so let's put it down here, A, this is B. For part C, what it's asking is the most probable speed. So if you look at the numbers here, we have 2, speed of 10, 7, the speed of 15. So this is so far the most number of particles that have this speed. 4, and then we have 3, and then we have 6. So this is the second probable. Okay, so the speed of 15 meter per second has the most probability. Therefore, this is the most probable speed. Section 3. Real gases and changes of phase. The curves here represent the behavior of gas at different temperatures. The cooler it gets, the further the gas is from ideal. So what we see, curve of A has the ideal gas behavior. As we can see, the dashed line is the ideal gas behavior. And as it's cooling down, the curve is going toward that direction, and it's deviating from the ideal gas behavior. In curve D, the gas becomes liquid. It begins condensing at little b. So here the gas is condensing, and it's entirely liquid at A, at here, at this point. At point C, we have a critical point, and this point is sometimes called triple point. This is the point where we can have the material at 3 stages of liquid, solid, and gas. Below the critical temperature, the gas can liquefy if the temperature is sufficient. Above it, no amount of pressure will suffice. So we have a PT diagram, pressure versus temperature, as we can see down here. This also is called a phase diagram, and this represents all 3 phases of matter into it. So solid liquid, which is this curve here, is melting or freezing. The liquid vapor curve here is boiling, and the solid vapor curve, this one, is sublimation. Here we're demonstrating a PT for carbon dioxide, CO2, and here we can see there is a point which is very special. It's called triple point, and this is the only point where all 3 phases can coexist in equilibrium. Okay, as an example, we look at problem 26 from the book. Water is in which phase when the pressure is 0.01 atm and the temperature is 90 degrees Celsius or B minus 20 degrees Celsius? So we should look at the PT diagram for water, and I have put it here. And let's look at what is the pressure and what are these pressure and temperatures corresponding to which phase of water. So at 0.001, which is, this is 0.006, so it should be 0.001, and the temperature is 90 degrees. So if we can go from here to almost 100, so it's 90 degrees Celsius here. this point. What is this phase? This is vapor phase. So this is gas. So this answer part A. So this is vapor. And how about minus 20 degrees? So the pressure is still 0.01 atm. And the temperature is minus 20. So this is 0. It should be minus 20 here. And this is the pressure. This is the point. At this point, the phase is solid. And when the water is solid, it means that this is ice. But state of matter is solid. Section 4. Vapor pressure and humidity. An open container of water can evaporate rather than boil away. The fastest molecules are escaping from the water's surface, so evaporation is a cooling process as well. You can consider this process when you have a hot cup of coffee or tea and you let it on the table, sit for a while, and then you notice that it's some smoky evaporation is coming out of the surface of the hot beverage, and you will see after a while, after the evaporation, you will see the level of the liquid will be a little bit reduced if you pay careful attention. And the reverse process, so the inverse process, is called condensation. And when the evaporation and condensation processes are in equilibrium, the vapor just above the liquid is said to be saturated, and its pressure is the saturated vapor pressure. The saturated vapor pressure increases with temperature. Here on the left, we have table 18.2. As we can see, for water, as the temperature is increasing, the saturated vapor pressure is also increasing. A liquid boils when its saturated vapor pressure equals the external pressure. If we go back to table 18.2 for water, we notice that the temperature of 100 degrees is the boiling temperature of water on the summit of Mount Everest. But if we go to lower altitudes, for example, if we go to the sea level, the boiling temperature of water drops down to 70 degrees Celsius. And that is an indication of less pressure requires lower temperature to start boiling process. Partial pressure is the pressure each component of a mixture of gases would exert if it were the only gas present. The partial pressure of water in the air can be as low as 0 and as high as the saturated vapor pressure at that temperature. Relative humidity is then defined as a measure of the saturation of the air, and we define as the ratio of partial pressure of water divided by saturated vapor pressure of water, and this is usually reported in percentage. So you must have felt this one, that when the humidity is high, it feels muggy and it is hard for any more water to evaporate. The dew point is the temperature at which the air would be saturated with water. And if the temperature goes below the dew point, dew, fog, or even rain may occur. Let's consider problem 36 from this chapter as an example. If the humidity in a sealed room of volume 420 meter cube at 25 C is 65%, what mass of water can still evaporate from an open pan? So to solve this problem, we have to look at the table 18.2 and pull up the saturated vapor pressure of water at 25 degrees C. And we know that saturation of vapor pressure of water at 25 degrees C from that table is equal to 3170 Pascal. And the amount of the water vapor that can be in the air can be found from the ideal gas law. So we call it PV is equal to nRT, and solve it for N, the number of moles of water molecules. And we know the pressure here is going to be 3170 Pascal times the volume, which we said 420 meter cube, divided by R, which is 8.314 joule per mole Kelvin, and multiplied by the temperature of 273 plus 25 degrees C converted into Kelvin. Pascal times meter cubed gives us joule, and Kelvin cancels out. These joule cancel out and K cancels out, and we have a 1 over mole in the denominator. So what we have at the end, if we simplify it, is going to be 537.4 mole. And since the humidity is 65%, from the equation for humidity, it means that only 65% of total possible water is in the air. It means that 35% can still be evaporated from the water stage into air and become gas, be added to the humidity to make it 100% of liquid gas or a water vapor. Okay, so we say mass that can be evaporated. Oopsie, what am I writing? The mass that can be evaporated is equal to 35%. Again, 65% is humidity. It means that 65% out of 100% is already in vapor mode. Now we have room for 35% to be converted from water stage of these 537 moles of water converted into, this is in mole, converted into water vapor. And we can convert from a mole into kilogram with 18 times 10 to the minus 3 kilogram per mole. And that gives us 3.385 kilogram, which is roughly equal to 3.4 kilograms. Section 5, van der Waals equation of state. So far we didn't consider the size of molecules, but here, to get a more realistic model of gas, we can include that. And we can include the finite size of the molecules and the range of the intermolecular force beyond the size of the molecules. So we assume that some fraction B of the volume is unavailable due to the finite size of the molecules. We also expect that the pressure will be reduced by a factor proportional to the square of the density due to interactions near the walls. This gives the van der Waals equation of state. The constants A and B are found experimentally for each gas. As we can see here, instead of P times V, instead of P, we have P plus a ratio of A divided by V over N squared. This is our replacement of the ideal case of P, multiplied by V divided by N minus B. And this is our V. Now has been reduced by V over N minus B. And on the right side we have R times T. So with the consideration of the finite size of atoms and molecules inside a gas, the pressure should be modified and be a little bit added to the constant pressure, and the volume should also be a little bit reduced because we're considering some sizes for the particles. Considering these modifications, therefore, we have a PV diagram for van der Waals gas, and it's deviating from the ideal gas, and it's fitting very well with most experimental data. All right, let's take a look at problem number 42 from the book. For oxygen gas, the van der Waals equation of state achieves its best fit for a parameter of A of 0.14 Newton meter to the power fourth divided by mole squared, and parameter B to be 3.2 times 10 to the power minus 5 meter cubed divided by mole. Determine the pressure in 1.0 mole of the gas at 0 degrees Celsius if its volume is 0.70 liter, calculated using the van der Waals equation as part A, and part B, the ideal gas law. Okay, so we start with the equation of van der Waals for part A, and we can write it down as P plus the parameter A divided by volume divided by N, number of moles squared, times volume V divided by N minus parameter B is equal to R times T. And if we can solve it for pressure P, we can write it as P equals to RT divided by V over N minus B minus A divided by V over N squared. Okay, so let's plug in the numbers, see what is P. 8.314 joule per mole Kelvin multiplied by 273 plus 0 degrees Celsius to Kelvin divided by 0.7 times 10 to minus 3 meter cubed divided by mole minus 3.2 times 10 to the power minus 5 meter cubed divided by mole minus, and we said parameter A is 0.14 Nm to the fourth divided by mole squared divided by 0.7 times 10 to the minus 3 meter cubed divided by mole, everything squared. And that gives us 3.1 times 10 to the 6 Pascal. Okay, and now for part B, so the pressure for van der Waals is 3.1 to the power 6. Now for part B, let's use the ideal gas law. So we say PV equals to nRT. Now let's solve it for P as nRT divided by volume. And if you plug in the numbers, you have 1 mole, R is 8.314 joule per mole Kelvin times 273 Kelvin, and the volume is 0.7 times 10 to the power minus 3 meter cubed divided by mole. And if we do the math, we will get 3.2 times 10 to the power 6 Pascal. And this is the pressure by the ideal gas law. As we can see, the value we obtained from the ideal gas law is almost 3% higher than the value we obtained from the van der Waals equation of state, and we're overestimating it with the ideal assumptions. Section 7. Mean free path. Because of their finite size, molecules in a gas undergo frequent collisions. The average distance a molecule travels between collisions is called the mean free path. So a particle shown here in blue is entering the mass of other particles. As we can see, starts by colliding the first particle, changes direction, hits the second particle, changes direction, third particle, changes direction, etc., etc., etc. But on average, the distance it travels from here to here, the average is called the mean free path. To calculate the mean free path, we should have the average speed, the density of the gas, the size of the molecules, the relative speed of the colliding molecules, and put them together, the mean free path, or L sub m. We can calculate it as 1 over 4 pi root 2 r squared divided by times n divided by volume, the number of atoms divided by volume. And r, little r here, is the radius of the molecule or the particle we are considering here. This is a representation of the size of the molecule. And v here is the velocity, mean velocity in a given direction. All right, here we consider problem number 46 from the book as an example. At about what pressure would the mean free path of air molecules be? Part A, 0.3 meter, and B equal to the diameter of air molecule, which is roughly 3 times 10 to the minus 10 meter. And assume the temperature is 20 degrees Celsius. To solve this problem, we look at equation A1810b, which gives the mean free path, L sub n, is equal to 1 over 4 pi square root of 2 r squared times n divided by v. And we need to find what's the number of particles at this temperature. And we should use ideal gas law. We call it PV is equal to capital N KT. And we can solve it for n over v as we need it here. And this is equal to P divided by constant K times temperature T. If you plug in these two equations together, L sub m, or the mean free path, is equal to KT divided by 4 pi root 2 r squared P. You can solve it for pressure, constant K times T, 4 pi root 2 r squared L sub m. So we can use this equation to solve it for part A and B. And here we say for part A, L sub m should be 0.3 meter. Solve P, plug in the values. K is 1.38 times 10 to the minus 23 joule per Kelvin. Temperature is 293, which is 273 plus 20 degrees Kelvin, divided by 4 pi square root of 2, 1.5. This is the diameter. Half of it is the radius, and here we have r, which is the radius. So we have to use r as the radius. 1.5 times 10 to the minus 10 meter, and it should be squared, times L sub m, which is 0.3 meter. If we do the calculations, we will get 3.4 times 10 to the minus 2 Pascal. So this is the answer to part A. And for part B, for L to be equal to the diameter of the molecule, P would be, so the numerator would be the same, joule per Kelvin multiplied by 293 Kelvin divided by 4 pi square root of 2, 1.5, 10 to the minus 10 squared. And then we have 3 times 10 to the minus 10. This is in meter, right? So if we do the calculations and solve it, we will get the pressure would be 3 times 10 to the power 7 Pascal, which is almost 300 atmosphere. At this pressure, the ideal gas equation is probably not a good model for the gas. So the answer, part B, is a very rough approximation. Section 7. Diffusion. Even without a stirring, a few drops of dye in water will gradually spread throughout. This process is called diffusion. Diffusion occurs from a region of high concentration to a region of lower concentration. In this diagram, or the figure cartoon down here, what we see on the left side has higher concentration, and on the right side we have less concentration, and here the direction of diffusion. The rate of diffusion is quantified as J, and it's equal to D times A times the derivative of C, which is the concentration, over X, or how much of the concentration we have over a given length. In this equation, D is the diffusion constant, and we have to have a lookup table, of course, and we have table 18.3 that gives us the diffusion constant D at a given temperature and pressure. Summary of Chapter 18. The average kinetic energy of molecules in a gas is proportional to the temperature. Below the critical temperature, a gas can liquefy if the pressure is high enough. At the triple point, all three phases are in equilibrium. Evaporation occurs when the fastest moving molecules escape from the surface of a liquid. Saturated vapor pressure occurs when two phases are in equilibrium. Relative humidity is the ratio of the actual vapor pressure to the saturated vapor pressure. The van der Waals equation of state takes into account the finite size of molecules. The mean free path is the average distance a molecule travels between collisions. Diffusion is the process whereby the concentration of a substance becomes uniform. And this concludes Chapter 18.